When we discuss electron configuration, I always like to bring up the energy level diagram. It kind of helps conceptualize how the periodic table is laid out in terms of orbitals and sublevels and energy levels. So when electrons fill the atom, it always fills according to the lowest energy level first, and the lowest energy level is the one that is going to be closest to the nucleus. So that's going to be the first shell, and each of these boxes represents an orbital, and each orbital can hold 2 electrons. So the first energy level can hold 2 electrons. Now the 2s and the 2p, we're going to talk about what s and p means in this video, but again, in total there are 4 boxes, meaning the second energy level can hold 8 electrons. Now we're going to expand on a previous idea here. In the past, we've thought that the third energy shell could only hold 8, but now when you count the boxes up here, it can hold a total of 18 electrons. So it's actually a little bit bigger than we think. It can expand when necessary, and then the fourth energy level can hold up to 32 electrons. Now, that doesn't mean they fill the entire fourth energy level. There are some energy levels here in between that need to be filled before we continue on and expand that third or fourth energy level, and we'll get to that in a few minutes. Now, the periodic table is laid out in such a way that allows us to kind of work from left to right, top to bottom, to write electron configuration. So things I like to point out here are the period numbers, and then also the letter that goes with each section. So you can see here that the pink section is S, and you can also see the helium on the right side is part of that. And then the middle section is the D, the right section is the P, and then this bottom section is the F. Now I'm going to go ahead and show you how to utilize the period numbers and the letters to write electron configuration. So if I were you, I'd find some sort of blank periodic table, print one out, or do one digitally so that you have this when writing electron configuration, because you will have to eventually memorize the different, period numbers, group letters, and all those things. So it's nice to be able to write it down so you can reference it. So when I'm going ahead to do electron configuration, I first like to organize my periodic table according to the periods. So I like to go ahead and label 1 through 7. I also like to go ahead and label 1 through 7 on the right side, because we're going to see that these numbers do fluctuate in the middle. So it's helpful to kind of remind ourselves what it is across the way. Now this whole section, as I labeled previously here, this is the S section. And then over here we have the P section. And then we have this middle area. Go ahead and kind of do this right here, and this is the D, and then we can go ahead and do this bottom section, which is the F. Okay, now the D section, I'm actually going to color in this over here to make sure you understand that's the S as well. The D section is actually one number less than the period it belongs to. So this starts with a 4S, you can see here, but we actually, when we get to this D section, it's going to be a 3. And then, so if you continue moving down here, you're always starting one less than the period that it belongs to. Now, another thing I want to point out is the F section. So remember this section from cesium, I actually may be saying that one wrong, CE to LU, remember it pops out from this middle area here after it's a part of the 6th period, and then number 90 to 103 pops out of 89 here. So again, these are still part of the 6th and 7th period, but they're actually F. So their sublevel letter is actually one less than the D. So this, remember, is 6S, and then we have 5D going along here. But this is 4, and then this one is 5. So we're going to go ahead and utilize this in a moment. You'll kind of see how this is laid out. But I always like to organize this on a blank periodic table when I was learning this so that I could utilize it during tests. And a lot of my students do the same thing. So let's go ahead and show you how this is going to be utilized. We're going to first go ahead and do arsenic, and then I will show you a shortened method as well. So again, our whole goal here is to get to arsenic, number 33. I'm going to go ahead and do my work right here. Now, you're going to start at the very top, and you're going to count the electrons, or you're going to actually count the number of elements we're going to pass by, and then indicate it by a superscript. So 1s, and there are 2 elements part of that. Okay, so 1s2 always starts us out. And again, this is going to correlate to that energy diagram on the previous slide, so you can always compare to that. We're going to continue 2s, And then there are 2 elements here that make up that section. So we're going to go ahead and write 2s2. And then go across to P6. And again, I'm getting that number at the top by just counting how many I am going across. And then continue left to right as you work your way down. So 3s2, go across 3p6 elements. And then we're at the 4s2. Now this is where that number comes into play. You're 1 less when you're in the D sublevel. So 3d. And if you count how many atoms there are in that, there are 10, or how many elements, and that correlates to how many electrons can fit in that subshell. And then 4p, and we only need to go over 1, 2, 3 to get to the arsenic element. So the way the periodic table is laid out directly correlates to the amount of electrons that fill the atom, because they increase as we go across, right? Each atomic number increases, therefore the number of protons, therefore the number of electrons increase. So each time as we're moving left to right, we are adding another electron and another proton to the previous element to create a new element. Therefore it adds to another sublevel or orbital, whatever correlates. So I'm going to go ahead and take this and move it down so that we can have that for reference on our slide. Okay, ignore all this mess going on here. All right, let's go ahead and try another one. So we're going to go ahead and work on PB. Okay, PB is lead, and this one's a little bit of a longer electron configuration, so make sure you save yourself room. And I'm not going to have you do a lot of these longer ones on a test, but I always want to practice one, especially since we're just learning this. We will then go back and do the noble gas or the shorthand method in a moment. All right, so we're going to start at the very top again. Our whole goal here is number 82, lead. So I'm going to go a little bit quicker here. So PB, you always start again at the top. 1s, 2 elements. Go down, 2s, 2 elements. Go across, 2p6. There's 6 elements. Like you're reading a book, left to right, top to bottom. 3s, 2 elements. 3p6 elements there. 4s, 2, 3d10, then you pop back to 4p6, then we're going head down to 5s2, the d's are always one number less than the period they're in, 4d10, 5p6. Now this is where it gets a little funky, so 6s2. Then from the 6s, you're going to have to remember this, it goes and pops down to the 4f. So it goes ahead and 6s2, 4f, and there's 14 elements that belong in that, or electrons that belong in that sublevel. And then we go back and do the 5d. So you have to remember 6, then the 4, then the 5d10. And then to get to lead, we're going to go ahead, and I'm just going to write this below because I ran out of room, 6p2, 2 elements over. Okay? Go ahead and copy that as well. Now let's go ahead and do a shortened method of this. Oh man, this is a mess, sorry. We're going to go ahead and do what we call noble gas, or you can call it condensed electron configuration. So to be able to do that, you have to be able to find the previous noble gas. And just to remind you, noble gases are on the periodic table, they are group 18. So in brackets, you're going to be putting the previous noble gas. Okay, so let's go ahead and look. We're looking at arsenic again. Our previous noble gas, I'm actually going to just work my way backwards here. So we're trying to do 33. Our previous noble gas will be number 18. So in the brackets, we can go ahead and put argon. Okay, and then you start your electron configuration right after that. So I know this periodic table is getting a little messy here, but you are going to start your electron configuration after your argon. So what comes next is your 4s2, okay, and then go on from there until you get to your intended element. 4s2, 3d10, and 4p3. Now a good check is you're always going to end kind of the same ending of a full and a noble gas. In case you're doing both, it's a nice check. So this is just the shorthand way. It allows you to kind of skip all this extra stuff from the very beginning and lets you start right from the noble gas. Now, you always want to read the directions to any question, of course, and it'll tell you either do the full or the condensed / noble gas, whatever way they like to refer to it as. I'm going to go ahead and do lead. So let's go ahead up and look what the previous noble gas to lead was. So it's number 82. The previous one is xenon, Xe. Remember, these are brackets, not parentheses. And then we're going to continue on with our 6s2, 4f14, 5d10, and we're going to finish with 6p2. Okay. Now, I just want to quickly show you, you can use electron configuration to figure out valence electrons. Valence electrons are the outer shell electrons. To do that, you're just going to go ahead and find your highest number, which is going to be your energy shell or your energy level. So in the case of arsenic up here, we can go ahead and see our highest number, which is the numbers in front, is this 4, and there's a second one. So you always want to make sure if there's more than one, you add them together. And then to figure out the valence electrons, you're going to only be looking at the exponents, and you add those together to get your number of valence. So arsenic would have 5. And you can use the condensed or the full to do this. Again, you'd still see the same 5. Let's do it again here for lead. And I'm going to review this a couple times in this PowerPoint. So if you look at lead's electron configuration, the highest number, so again, I'm talking about these numbers here. The highest one I see is this 6. And I'm going to look and make sure, oh, there's another 6. So I'm going to go ahead and add both of these electron numbers here. So we can go ahead and add those together. And that makes our number of valence electrons for lead to be 4. Okay. Now, another tip here, when you're doing electron configuration, you can add up all the exponents and you will get the atomic number of the element you're working with. So it's nice to be able to kind of check at the very end to make sure you didn't forget any of the numbers. So if you added all these exponents up for arsenic, you would get 33, I believe, is arsenic's atomic number. Okay, so how electrons fill orbitals. And again, orbital is just another word for a probable location of finding an electron. We draw boxes for orbitals to indicate that. And we're going to talk about the arrows and all that as we draw these sort of diagrams. Now, I just want to remind you, you will have to have these rules memorized. Of course, not verbatim, but being able to point out a mistake and say, hey, this is Aufbau or this is Hans or something like that. So when we are drawing what we call orbital diagrams, so this is very similar to electron configuration. So instead of writing 1s2, we do orbital diagrams and we do a box and then we show an up-down arrow, and we'll talk about that up-down arrow here in a second. That's an example of a Pauli exclusion principle. But instead of writing 1s2, we write the 1s and then we put a box and we use arrows to demonstrate the electron. So again, instead of 2s2, we would see these arrows. Now, the reason why we're always going to start at 1s, just like we do every time we do electron configuration, is due to Aufbau's principle. And Aufbau's principle means that electrons fill the orbitals in order of increasing energy, which is why I like that energy diagram on our first slide. So it's always, 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 always going to start with 1s. It's going to be completely filled with 2 electrons before we move to the 2s, where it's then going to completely fill. You're never going to just see one arrow or one electron in there because you need to fill it before you move on. Okay, before you move on to the next higher energy level. So that's Aufbau. Now the next one we're going to go ahead and look at is the Hans rule. So we have in the 2p, or really any p or d or f orbital, we have multiple orbitals here. So this whole sublevel has 1, 2, 3 orbitals. Now Hans rule tells you that you are going to put electrons into separate orbitals before you double them up. So what that means here is you are going to, when you draw your 3 boxes, or I'm going to practice drawing these in a few minutes here, but each one of these boxes is going to get 1 arrow in the same direction before you fill them. So just think about this. If you and your sibling, your family was moving into a new house and your parents said, do you want to live in the same bedroom or do you want to have your own bedroom? You'd most likely choose your own bedroom, right? So therefore, that's what electrons would do. They want to choose their own space, their own orbital before they double themselves up. Now, if they do double themselves up, which you can see happening here, Then we refer to the Pauli exclusion principle, which means that within one orbital, electrons must have opposite spins. So to demonstrate opposite spins, we go ahead and put an arrow in the other direction, okay? So it'd be kind of like putting your beds on opposite sides of the room. Now, the reason why this happens is, remember, electrons are negative. They have a negative charge. And for them to coexist in the same space, they need to actually be spinning in directions that allow the repulsion to be minimized. So we do this by seeing them flipping themselves around. So we're going to go ahead and utilize these 3 rules as we draw orbital diagrams here. Now again, orbital diagrams is just another way to demonstrate electrons and where they exist in the atom for any single element. So here we have the electron configuration for chlorine, and you can go ahead and verify that. And then what we're going to now put this into is orbital diagrams. And an orbital diagram still shows the sublevels, but instead of putting the exponents for the electrons, we use arrows to represent the electrons. So an up and a down arrow, again, you never going to have two of them being up or 2 of them being down due to the Pauli exclusion principle. You're always going to have them have opposite spins, and we use an up and down arrow to indicate that. So every time we have any sort of S, a 1s, a 2s, a 3, so on and so forth, we draw one box. A box represents an orbital, and so each orbital can hold 2 electrons. So any S sublevel can hold 2. Any P can hold 3 orbitals, a total of 6 electrons. When you draw these, you're always going to draw all 3, even if you're not filling them. Even if you're not filling them, you still need to show the available options. Any D, which we'll see here in an example, has 5 orbitals or 5 boxes, which can hold a total of 10. Any F can hold 7 orbitals, and therefore 14 total electrons. So let's go ahead and draw an orbital diagram for silicon. So silicon, you want to go ahead, why don't you practice here and write the electron configuration for silicon so we can go ahead and utilize this. It's not necessary for orbital diagrams, but it's a good way to start practicing. So 1s2, 2s2, 2p6, 3s2, 3p2. Now we're going to go ahead and transfer that to an orbital diagram. And so what you do is you write the sublevel 1s, and you can draw a box or just a line. I'm going to just do a line. It saves some time. And then how we draw is an up and a down arrow. Now to save time, we usually do half arrows, but there are so many options of doing this. If you've done this with a circle or an X, I'm totally open to other options as long as you stay consistent. You're welcome to check in with me about that. So 2s, again, completely filling it. And then we're moving on to the 2p. The difference here is you are not going to see a number of exponents. You're not going to see that, right? You are demonstrating the electrons by using the arrows. So no exponents. We're just labeling each grouping of orbitals. 3s. And then 3p. Remember I told you want to draw all the options. Even though we're only filling 2 of them, we are going to show them all. Now again, what we're not going to see here is 2 in the same, right? You want to have your own bedroom before you're going to double up. That's Hund's rule. So we're not going to see that. You're going to make sure you put them in separate. So this is the orbital diagram for silicon. We call these unpaired electrons, and we call these paired electrons. We're going to be talking about that in a little bit, so I wanted to point that out. So let's try this for cobalt now. Cobalt is CO, number 27. I'm going to go ahead and not do the electron configuration. You can, of course. I think it's helpful when you draw these, but I'm just going to go right ahead and do this. So 1s, 2s, 2p, 3s, 3p. I'm already writing too big here, so I'm going to have to cram it in. Then we have 4s, and I kind of ran out of room, so I'm going to go ahead and do our first D, which is 3D. 1, 2, 3, 4, 5. And to get to cobalt, 1, 2, 3, 4, 5, 6, 7. 7. So 1 fills each one of these, and then we double up for 2 of them. Okay? So again, that is our orbital diagram for cobalt. So again, we always start at the 1s. That is Aufbau's principle. We have opposite spins or opposite arrows. That is Pauli exclusion. And we fill each one independently before we double it up. That is Hund's rule. Now, I referenced earlier the difference between valence electrons and using the electron configuration to figure that out. If something is written in electron configuration and it is not a valence electron, then it is called a core electron. So look to the top right corner here. You can see chlorine being represented, the Bohr diagram. So anything on this outer shell here is considered a valence, and then anything in the inner shell here, which is basically everything else, is considered a core electron. So we're going to go ahead and, we're not always going to have these Bohr diagrams though, so we want to make sure we can understand how to utilize our electron configuration for this. So if I have the electron configuration for neon here, you can see neon. Let's go ahead and indicate our core and our valence. So our valence is always going to be the highest number in front. So I see a 2 and I see a second 2. And then I'm going to actually only utilize the exponents to get the valence. So you add those together. And so we have 8 valence. And then if it's not valence, the only other option is that it's core. So we have 2 core electrons and we have 8 valence for neon here. Okay. Let's go ahead and try this again for selenium. Selenium is number 34. So I'm going to go ahead and write the full electron configuration for this. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. So let's go ahead and figure out our valence electrons. Our valence electrons, we're going to be utilizing the highest energy level, which are the 4s there. So I'm going to go ahead and add those exponents up. That gets me 6 valence electrons. So 6 valence electrons. And then how many core is basically everything else here, which I'm just going to indicate here by doing this. And to figure out how many core, you could just add up all of these exponents, okay, which I'll let you do, and the rest of those are core. So they're either valence or core. Now we're going to go ahead and figure out a quicker way to do electron configuration, or excuse me, a quicker way to figure out valence electrons by utilizing just where it's located on the periodic table. You're going to love this. So what I have here is Bohr diagrams for elements 1 through 18. And the way I did this was actually kind of took out this middle portion of the periodic table. So please recognize this is groups 1 and 2, so hydrogen and beryllium groups. And then we skipped that center transition area. And now the rest of these are 13 through 18. Okay, so we are skipping that center section. And so the trick for this, the valence electron trick, only works for groups 1 and 2, 13 through 18. And it works for things below this. It's just I only had these to kind of demonstrate it to you. So what we're trying to figure out here is what trends can we use to indicate and figure out electrons, the valence electrons specifically, quickly, without having to do orbital diagrams or valence, numbers using electron configuration. So what I'm going to look at here is utilize my pictures. And so when I look at group 1, I can see how many valence electrons everything in group 1 has. So hydrogen has 1 valence, lithium has 1 valence, sodium has 1 valence. Okay, so 1 valence electron for everything in group 1. Everything in group 2 has 2. Okay, so 2 valence electrons. Let's look at group 13. Group 13 has, boron has 3, aluminum also has 3. Okay, so 3 valence electrons. Group 14, 1, 2, 3, 4, 1, 2, 3, 4, 4 valence electrons. Group 15, hopefully you're starting to see the pattern here, okay? So we can utilize our periodic table in terms of going down the groups to figure out the valence electrons. So let's actually add that to a periodic table and try a practice example of this. So the trick is utilizing the group number to do this. So everything in this first group here has 1 valence electron. Okay, everything in group 2 here has 2 valence electrons. And then again, we're going to talk about this middle section at a later date. Actually, I believe it's maybe possibly on the next slide here. But right now we're just going to focus on 1 and 2, 13 through 18. So then the boron group, group 13, has 3 valence electrons. I'm going to go ahead and fill this in. 4 valence, 5 valence, 6, 7, and 8 valence for everything in group 18. Now, how could I utilize this? What if I asked you quickly, how many valence electrons does antimony 51 have? You'd say, it's in group 15, therefore it has 5 valence electrons. Everything in this group has 5 valence. Let's try another one. If I asked you how many valence electrons barium has, barium is in group 2. It has 2 valence electrons. So it's really, really handy instead of having to write out the electron configuration. Now let's talk about why this doesn't work for the center section, the transition metals, group 3 through 12. So to do that, let's write the electron configuration quickly for copper, and then we will see why the trick doesn't work. So 1s2, 2s2, 2p6, 3s2. Okay, and copper has 3d9. Now, the reason why we cannot use a trend here is because transition metals and those in the lanthanide and actinide series, their highest energy level is always, and I'm actually going to reference it by looking up here, is always going to be these two groups, okay, because their number is 1 higher. So remember, this is like 4 S, this is 3D, this is 5S, this is 4D. So the higher shell, you can see that right here, the highest shell for transition metals is the one that is previous, the previous S. So this S, therefore, is always going to be our number of valence electrons. So for copper, if I asked you how to find the number of valence electrons, you'd utilize this, and you'd say, okay, this has 2 valence electrons, because the highest energy level, which is the 4th energy level, only has 2 electrons in it. Let's go ahead and do another example for yttrium. And to do this, I'm actually going to just do the noble gas electron configuration. Yttrium is number 39. So I'm going to go ahead and do the previous noble gas, which is krypton. And then I'm going to go ahead and start, which is 5, S2, 2, 3, 4, 5, and then 4, D1. So the same example here applies. You can use the shorthand or the full electron configuration to do this. But again, this transition metal, its highest energy level here is the 5s2. Therefore, it's going to also have 2 valence electrons. Now, for any atom, so same number of protons and electrons, the valence electrons are going to be the same, probably 2. Now, when we start to get into ions, we're going to see how that changes. But for right now, most of the middle atoms, the transition metals, have 2 valence electrons. So let's go ahead and practice this concept. So I'm going to go ahead and do the electron configuration for phosphorus and for gallium, and then we're going to go ahead and find the number of valence electrons. So I'm going to kind of speed through writing these. And the only way you'll get better at this is practicing it, so don't hesitate to pause and then check your answers. And then the number of valence electrons is the highest energy level, which is the 3rd, and I add these together and we get 5 valence. Okay? Again, you don't have to show that on there. I just wanted to demonstrate that. All right, and then gallium here. 1s2. Okay, so again, my highest here is the 4s. Add those together, and I get a total of 3 valence for gallium, which works with our valence electron trend. Okay, so you can always check your answers, but when I'm asking you to look at it in terms of electron configuration, please make sure you utilize what you have in front of you. All right, so let's go ahead and practice some figuring out like mistakes in electron configuration or orbital diagrams here. Which of the following electron configurations or orbital diagrams are allowed and which are not? And let's talk about why there is an issue. So I see 1s2, I see 2s, and I see a 1 right here. So it is not allowed because you cannot move on to the next one without this being a 2s2. We call this an off-BAW. Hopefully I spelled that right. Violation, off-BAW rule violation. So it has to be 2s before it moves on. So let's go again, look here, 1s2, 2s, same issue here. It needs to be 2s. But I also see another issue. 2p can only hold 6. So that's another off-BAW violation. And then I don't know if there's a violation for having, you can't even have too many. So 2 mistakes in letter B. Let's check letter C, 1s2, 2s2, 2p6. Okay, so it looks good, except for the fact that before you can go from 3p to 3d, you have to fit in a 4s2. So this is actually considered an off-BAW violation as well, because you skipped a sublevel. So 1s2, there's 2. Okay, so again, we're seeing the same thing. We need a 4s2 here. And remember, the Ds can only hold a total of 10. And then letter E, hopefully you can clearly see this one. The 2s is a violation of the Pauli exclusion principle. It should have an arrow up and an arrow down. And remember, circles work. A lot of times people will do squares as orbitals. Sometimes you will see circles with X's. There are so many different ways to represent orbital diagrams. All right, one of the last concepts we're going to talk about in this is the magnetic properties. So if you've ever wondered why something is magnetic and something is not, here is the time to answer that question. So although electrons behave like tiny little magnets, two electrons that are opposite in spin cancel each other out. So again, opposite in spin is represented by an up and down arrow. And so only atoms with unpaired electrons can exhibit magnetic properties, basically. Okay, and so we have to use an orbital diagram to be able to figure this out. So we have two terms. We have paramagnetic and we have diamagnetic. Paramagnetic is one that is weakly attracted to a magnetic field because there are unpaired electrons. Okay, so we say this is magnetic. And diamagnetic is not magnetic. It's not attracted by a magnetic field because there is only paired electrons. Okay, only paired. So again, every one of them would be an up and a down arrow. Whereas the paramagnetic, you would see some that are maybe only one up or one down, depending on what way you've done it. So let's practice this. Is this metal magnetic? So to do this, let's go ahead and draw our orbital diagram. You may need to do the electron configuration before you do the orbital diagram, and that's perfectly fine. So I'm going to go ahead and I'm actually just going to do the, I'm going to do a orbital diagram quickie version here because we've been doing quite a few of these. So I'm going to go ahead and put argon in brackets, and I'm going to cheat and go ahead and do the 4s and then the 3d. Remember, D has 5 orbitals, and so iron is 1, 2, 3, 4, 5, 6 elements in. So 1, 2, 3, 4, 5, 6. So you can see here there are 4 unpaired, meaning it is, let's see, unpaired means this is paramagnetic. So iron is magnetic. Now there are definitely things that are more magnetic versus less magnetic. We're not going to do that in this class. We're just going to kind of be black and white. Is it magnetic? Is it not? But I do want to let you know the more unpaired, the more magnetic it is. So I find that interesting. All right, zinc. Let's go ahead and do zinc. I'm going to go ahead and also do the shorthand here. So we have argon, and then we have the same 4s, and then we have 3d. And there are 10 electrons. So all of these are actually paired up. So therefore, there are no unpaired electrons. These are all paired. Therefore, this is dimagnetic. So zinc is not magnetic. Okay? And so here is a quick little orbital diagram for the first 10 elements. And we're going to say if this is magnetic or not. So I'm going to put a P for magnetic because it stands for paramagnetic, and then I'm going to go ahead and put in D for dimagnetic, which means that it is not magnetic. Okay, so hydrogen has an unpaired electron. Okay, meaning technically, I guess it would be magnetic. Most likely, hydrogen is not magnetic, but that's okay. We usually only do this for transition metals. But all right, helium has no unpaired electrons. Again, remember, even though these are blank, they're not unpaired.